We can classify materials into two different classes. I mean, you can classify materials into many different classes, but here we're selecting two. So the one way that I can separate materials is if I apply a force in any direction, just applying the same force in any direction, I'm going to get the same strength. Same strength. So strength in my sense that is like the same force required to break it. Yeah, assuming that there's the same areas, same dimensions, everything. Yeah. Or I can have a material that doesn't do that, where it requires more strength in a particular direction, and less in others, to break the material. Yeah, so it doesn't require so much to break material in this direction, but much more in this. So different strength. The technical terms for each of these is that this is what you call isotropic, and this is what you call anisotropic. Anisotropic. So an is like the opposite. Iso means same, so same direction. So yeah. So yeah, every direction. Same strength. Different directions. Yeah. For this one, it's different directions, different strengths. Different directions, different strengths. Yeah. So that's just something that it might be useful for you to know. Something like memorizable for the exam. Yeah. Okay, so going on further. Now, different materials have different grains or alignments in different ways. Some materials you can visualize them as like a stack of papers. So a stack of papers being aligned in a certain direction. Maybe it so happens so that it aligns in the same direction as the specimen itself. So I'm trying to draw straight lines, but I kind of suck at that. Yeah, right? They're all aligned to the material. Or it could be such that the material is cut so that it's in a different direction. Now these both, because the planes are aligned in different directions, they're going to have different strengths. So it's going to require a different amount of force, and they're going to react differently as well. So what I could do with these in this sort of situation is that, say if I isolate one plane, so this is my specimen, yep, isolate one plane. Now that force that I'm applying, it can be resolved into a resolved tensile force and a resolved shear force. So that tensile force is splitting the planes away from one another. So it pulls the planes away. And then the shear force is the part that makes the planes slide across one another. Yeah. So I can make a resolved shear force and a resolved tensile force. Yeah. Maybe one is weaker than another, and so you need to consider both. What? Okay, forget that. So simply put, the formulas for each of these is that this amount is what you, yeah. So take this as the original area, and then the force that I'm pulling, call that F. Still same area, same force. Yeah, there's force there as well. Yeah. Simply put, I'll put the formulas out here. The derivation will come in another video. So the resolved shear force. Yeah, the resolved shear force, so this amount, and this I'll call this resolved shear force. Yeah, resolved tensile force. Sorry, resolved tensile stress. Technical terms. Is equal to the original stress, which is just the force on the area. So this one. So F over A times cos squared of the angle, and the angle is from across to the horizontal. Yeah. and my resolved shear force is going to be the original tensile force times cos theta sine theta. So these are just the formulas that you would need to know. Get that, like, sometimes you might be given in an exam, sometimes not. It's always a good idea to get this underway. If you want a derivation to help it sink in, I'll make another video on this.